for hyperspectral image classification. NIT Raipur is an institute of national importance in Raipur, in Chhattisgarh state in India, and it is fully funded by MHRD. And it currently offers BTech, MTech, MC, and Applied Geology and PhD programs in all disciplines of engineering, science, humanities, and social science. BTech admissions in this institute is through JEE, which is conducted by JOSA. MTech admission.
It will be better if you switch directly to your presentation.
Okay, sir. Okay. Sure, sir. These are some topics which I will going to discuss further in the slides. First is introduction, then literature survey, and the method that we have proposed, then the results we got from this method, and conclusion and references. So let's see some basics of hyperspectral image. Hyperspectral imaging is the collection and processing of information from across the electromagnetic spectrum. In HSI, one continuous spectrum is measured for each pixel from the visible to near infrared wavelength range of 400 to 2400 nanometer. Human eyes see visible lights in 3 bands, that is red, green, and blue, whereas spectral imaging divides the spectrum into many more bands. HSI analyzes a wide spectrum of light instead of just assigning primary colors to each pixel. It is a high-dimensional image cube, which can be considered as a stack of images with different wavelength intervals. And HSI classification is the task of correctly predicting the different pixel values associated with different classes present in a remotely sensed image. And some uses of HSI are in distance measurement studies in research fields like agriculture, forestry, land surface mapping, etc. So these are some basics of convolutional neural network, or CNN. CNN consists of 3 layers. First is convolutional layer, pooling layer, and fully connected layer. In convolutional layer, a filter or kernel will move across the whole image, and the dot product is calculated between the input pixel and the filter. As it can be seen from the image here, that this is the input image and these are the filters, and we got the output by calculating the dot product, and this output is called as feature map or activation map. Then after that we have pooling layer. Pooling layer, it conducts the dimensionality reduction, and it helps to reduce complexity and increase the efficiency of the image. And at the last, we have fully connected layer. This is the fully connected layer. In fully connected layer, each node in this directly connected to each and every node in the previous layer, and it performs the task of classification by using its activation function. 2D CNN does not give the spectral features of the image. It only accepts the spatial features for each pixel for classification. And hyperspectral pixels have rich in spatial as well as spectral information. So wavelets are used for extracting the spectral information from the image. Wavelets are functions that are concentrated in time as well as in frequency around a certain point. And wavelet transform is designed in such a way that it gives good frequency resolution for low frequency components and high temporal resolution for high frequency components. And computing wavelet transform is very lighter. So wavelet CNN uses layers of wavelet transform to bring out spectral features for HSI classification. These are some literature surveys. In paper 1, A. Tariq and others proposed a 3D CNN, which is followed by 2D CNN. In paper 2, F. Malgani and others evaluated the capabilities of SVM classifiers in HSI. And Y. Shen and others uses 3D CNN for feature extraction. R. Vaddi and others proposed a model which uses probabilistic PCA for feature extraction, and classification is done through CNN in their model. X. Yang and others proposed 2D CNN, recurrent 2D CNN, 3D CNN, and recurrent 3D CNN for the task of classification. A. Mohan proposed hybrid 2D and 3D CNN. S.K. Roy proposed a model named hybrid SN, which is a hybrid spectral net, which is basically 3D CNN, then followed by 2D CNN. A. Plaza uses SVM and TSVM for classification. And here RJ uses 3D CNN. S. Fujita uses wavelet CNN for classification. O. Huashi and others proposed a DSVM, that is deep support vector machine, for HSI classification. T. Chakrabarti uses 2D CNN with wavelet CNN. R. Heng uses cascaded RNN model, and TV-Vandos uses LDA with 2D CNN. And in all these methods and papers, benchmark datasets like Selna-Seen, University of Pavia, and Indian Vines are used for evaluating the performance of the model. This is the architecture of the model, of our model. Here, this is an image cube of dimensions 512 cross 217 cross 204. That on that factor analysis is applied for the dimensionality reduction. And the reason why we have used factor analysis is that it is able to describe variability and among the different correlated and overlapping spectrum bands, which help to classify similar examples better. Then the output we got is here, which is 512 cross 217 cross 3. And from that, patches of size 24 cross 24 cross 3 are extracted. And on these patches, 4-level wavelet decomposition is applied. Then we have multiple convolutional layers uh, for extracting the features, and these circle shows the concatenation. So suppose here the output from this convolution layer and the output from this convolutional layer is concatenated and given as the input to next convolution layer. And at the end we have average pooling with a pool size of 7 cross 7 and a stride of 1. Then we have two dense layers and two dropout layers, and dropout of 0.4 is used. And at the end we have classification layer with 16 nodes, and the model is trained over 60 epochs with a learning rate of 0.01, and stochastic gradient descent is used as the optimizer. So the dataset which we have used for evaluating the performance of our model is Selena-Seen dataset. It consists of total 16 classes with 512 cross 217 spatial dimensions and 224 spectral bands. It has total of 54,129 samples, and from these total samples, 10% is used for training, that is 5,412, and remaining 90%, that is 48,717, is used for testing purpose. This table shows the class name of the total 16 classes and the training samples from each class, and the last column shows the testing sample from each class. As I have said earlier, that 10% from each class here is used for training and remaining 90% is used for testing. This table shows the class-wise accuracy that we have obtained by using softmax as well as sigmoid as the activation function in the classification layer. And from this table, it is clearly seen that we have got an accuracy of between 99 to 100% for all the classes. This is the training loss. A is the training loss graph during the training period of the model, and this is the training accuracy graph. And from this figure A, it can clearly be seen that the training loss reduces significantly as number of epochs increases. This is the ground truth image of the Selena-Seen dataset, and figure B shows the classified image that we have got by using the wavelet 2D CNN model of the same dataset. This table shows the comparison between the two other state-of-the-art approaches and our model. First one is hybrid deep ResNet and inception model for HSI classification, and the second one is HSI classification based on semi-supervised 3D deep neural network. The average accuracy that we have obtained is 99.88 and 99.85% by using softmax and sigmoid respectively as the activation function, and the overall accuracy that we have got is 99.87% in case of softmax as the activation function, and 99.67 in case of sigmoid as the activation function. And we got an Cohen-Kappa score of 99.85% and 99.63% respectively. And it can also be seen from this table that our model performs better when comparing with these other two models. So the conclusion is that in this a hybrid wavelet 2D CNN model is proposed for the HSI classification, and the Selena-Seen dataset is used for evaluating the performance of the model. And this approach takes both the spectral and spatial information for the classification, and the results that we have got when compared with other state-of-the-art approaches depicts that our model performs better. And while implementing our work, we found that the future work can also be done in this by experimenting and implementing it with other classifiers as well as different data sets. And the approach is lighter than the 3D CNN. These are the references that are referred. Thank you. Thank you all.
Apur,
Yes, sir.
what was the reason of selecting wavelet CNN?
Sir, because wavelet, as we have used wavelet for extracting the spectral features, because 2D CNN only gives the spatial features of the image. So that's why, as hyperspectral images are rich in spatial as well as spectral features, so wavelet are used for to get the spectral features from the image, and it is very computationally lighter. So that's why we have used the wavelet.
So first you are moving into the frequency domain by applying the wavelet transformation, and then you are applying CNN, or you are simply extracting certain features from the wavelet and then you are applying CNN.
So
What is it like?
We are extracting features by using wavelet and then we are applying CNN.
So while you would be moving into the frequency domain by applying the wavelet transformation, so you would be getting an approximation component and 3 high-level signals, which are nothing but the horizontal, vertical, and the diagonal edges that you would be getting out from the wavelet transformation.
Yes,
so you are considering these 4 edge types of edges and then applying a CNN over it.
Yes, sir.
And how many, what was the size of the convolutional layers?
Sir, size, kernel size, sir? Are you asking?
No, I'm not asking the kernel size. How many times you are applying the convolution?
Sir, 14 times.
14 times. So that means you are blurring the image more and more. The higher is the number of levels that you are applying, so you're performing more of the blurring. So I just wanted to know whether the problem, the model is facing the vanishing gradient issue or not.
No, sir. The model is not facing any such issue, sir.
No, I hope you are familiar with this term, vanishing gradient.
No, sir. Sorry, sir.
Okay, so I'll make it simplify the things. So it is like when you are doing more and more of convolution, a time will come when the higher layers that you are convolving now won't be creating any similarity or dissimilarity between the previous layers. That means the weight change is not significant that you are trying to learn through the back progression. So that is not significant. So are you sure that your model will not suffer from this particular problem?
Sir, in the model, we have concatenating the output of different convolution layers. So I don't think so that the model suffer from this problem, because we are not applying convolution layers simultaneously. We are basically the output of 2 convolution layers and concatenate them and given as input to the other convolution layers.
Okay, Apur.
Thank you, sir.
So any more questions from either session chair or from the participants?
Yes, Apur.
Yes, sir.
In this data set, you used for the testing purpose.
Yes, sir.
Balance or it was imbalanced?
Yes, sir. Please repeat the question, sir. Sorry, sir.
You have used the data set for testing purpose. It was balanced or imbalanced?
Sir, it was imbalanced. Means only 10% are used for training, and the remaining 90% are used for testing.
So how do you handle this imbalanced?
Sir, this is the limitation with this data set, HSI data set, because the labeled samples are very less in case of HSI, but one sample is enough. Means one sample contain large number of spectral features, so one sample is enough to distinguish the objects from one another. And it is also a challenge that we have to train the system with these limited labeled number of samples, and the model will perform better.
One more question is there.
Yes.
In hyper spectral images,
Yes.
they are having this three-dimensional structure, right?
Yes, sir.
So why you not considered 3D convolution neural network?
Sir, because the computation of 3D convolutional network is very high. Means computation wise, it consumes more resources and it takes more time as compared to this wavelet CNN.
Okay, thank you.
Thank you, sir. Thank you, sir.
Thank you, Mr. Apu, for your presentation. And
Yes. Thank you, sir.
now I request next paper ID 279, Mr. Prashov Gadza, to present his presentation.
Am I audible?
Yes, sir, you are audible.
Is my screen visible?
Yes, your screen is also visible. Please start your
Good
presentation.
afternoon, everyone. I'm Pranshav Gajjar, and I'm going to present our paper, which focuses on the empirical analysis of hybrid neural networks. And from hybrid neural networks, I'm implicating a parameterized variational circuit, which gives a standard network quantum enhancements. And we have used all of these technologies for classifying and understanding synthetic aperture radar data. The table of contents, this presentation would follow the standard scenario, and we're going to proceed with the background. So from the modality of papers or the modality of research available to us, it's extensively clear that synthetic aperture radars or SAR data are notoriously difficult to understand. And when it comes to the dimensionality, or when it comes to classifying them through a mathematical function, a lot of parameters or a really computationally expensive scenario is obtained, and you need to train extensive networks, and you need to train really large sets to get an accurate reading or to get an accurate understanding of what your initial values were. And from the advents of deep learning, or through our recent advancements, there are really developed neural networks or really developed convolutional networks which help us perceive how images travels. We have networks which are specialized for SAR. We have generative networks which help us create more data. So the predicaments associated with a standard data sets are gone, and the only advancements that really remain are creating better models which are able to acquire a higher effective dimension. Now, the term effective dimension is incredibly important here and is the basis of our study which we are presenting. So considering the ancient research or how things proceeded before today, we had papers, we had research which focused on the aspect of data for machine learning algorithms. They focused on improving their data sets. They focused on improving their data quality to get a better performing model. But a relatively sparse research exists when we consider the model space. Now, the effective dimension can be understood as the set of different model characteristics or the set of different model types that your particular architecture would assume or would occupy in the totality of the model space. So if you have a particular algorithm that has a higher effective dimension, you can say this intuitively that the model would generalize well because it contains the caliber to understand and represent a larger amount of data. Or it can have a better latent representation, or it can have a better spatial awareness when it comes to image manipulation or when it comes to data manipulation. So from that motivation, that is improving the effective dimension for standard networks, and to classify what's synthetic aperture radars or SAR data, we have worked on the amalgamation of classical networks and quantum neural networks. Now, quantum neural networks can be understood as a parameterized variational circuit. So you have qubits which act as neurons, and they would be functioning as what you would consider the representations. So through time, the parameterized circuit is trained and it works in conjunction with your standard network. And we test how this particular algorithm pans out with other architectures and with other algorithms that exists in our current literature. Now, from our literature survey, the two main papers which inspired this paper were, number one, the power of neural networks, which has been published in Nature and explains us how quantum enhancements or quantum neural networks acquire a better dimension in the model space. And we also have a paper which worked on combining quantum neural networks to classical neural networks. So you would have a standard encoder strategy or a standard fine tuning network where you would have a pre-trained network which occupies the previous layers, and you would add a multi-layer or an MLP or a standard feed-forward network to classify or categorize those latent representations learned by that pre-trained network. But instead of just using an MLP or a feed-forward network, we replace that with what is called a quantum neural network. Now, to test out our theories or to test out our algorithms, we use the standard MSTAR dataset. Now, MSTAR stands for Moving and Stationary Target Acquisition and Recognition, and it was developed by DARPA and the SNL lab. Now, for our studies and due to the computationally expensive nature of quantum networks, we have chosen two specific classes called BMP2 and T72. So the image represents how these objects exist in our data set and what they look like in real life. So it's extremely difficult for a normal person to understand them or to understand those features. But as we know, neural networks do shine here. And through experiments, we'll also understand how quantum networks pan out in this situation. Now, before, we are combining a parameterized variational circuit to a standard network. And 4 different permutations exists. So you would have the encoder, which is a network trained on ImageNet or a pre-trained network which contains those ImageNet weights. The top layers are removed. So we have the latent representations, and those latent representations are fed into an MLP, are fed into the quantum network, which contains the same architecture as that MLP to have an unbiased research. We also have tried to fine tune them instead of just using those latent representations. And through time, the whole weight, the weights are changed for the whole network, and you get a better generalized model, which is the principle behind fine tuning. And we've also compared it to the standard encoder, that is a network with those ImageNet weights, which gives us a better initialization than just assuming random weights. And those models are trained on this data set in a standard manner to actually compare how these algorithms pan out or how quantum enhancements pan out. And through experiments, a dilemma was obtained that we weren't able to accurately categorize them because different results were obtained for our ResNet and DenseNet encoders. So we also introduced what is called HQuantSN, or a network induced with fire modules, which were developed by the SqueezeNet paper. And these modules enable us to reduce the total number of parameters and get a better comparison of how a quantum network would work if the latent representations were sparse, or if we had a lower dimension of representation or a lower quality of representations. Because the principle of fire modules is to obtain a trade-off in your accuracy or in your classification tendencies and your total time. So they reduce the dimension significantly, but they do not give you the best result. So when we experimented thoroughly with them, it was seen that a standard ResNet was giving you a superior performance with the 99.61% accuracy. But when it came to DenseNet, DenseNet with quantum enhancement outperformed the other variants. And as we can see, the result is pretty similar, and we're getting a stellar accuracy which rivals the state of the art. And when we compared the HQuantSN and the standard SCN, which is the SqueezeNet, it was seen that the quantum enhancement didn't perform as well. So it can be inferred that in situations which provide us a minimal latent value, or where the encoder is relatively weak, it's not as good as the ResNet or it's not as good as the DenseNet, quantum enhancements won't be extremely viable, but they still offer you a better dimension, a better effective dimension. So they have their utilities, but a paper basically explains you when and when to use a quantum enhancement or how to do that. And for our experimental apparatus, we use the standard online platforms which allow us to use deep learning algorithms like Colab and Kaggle. We also tested our algorithms on a standard benchmarking PC, which was available to us. And we have used the PyTorch API along with the PennyLane API, which helps us simulate qubits, or which helps us create this parameterized circuits. As I mentioned, the use of quantum networks is clearly shown here. It's clearly visible that quantum enhancements or parameterized circuits have significant utility, and they should be used, but there are specific conditions which are associated with them. So if a problem statement exists which contains complicated data where standard networks do not give you the desired result, using a quantum enhancement might be the only feasible solution. They do require better computation, or they have expensive computation needs, but a trade-off can be obtained, which would be viable for a lot of applications. As I mentioned, the main papers which molded our research or inspired our research. And thank you. Are there any questions?
Pranchal, can you tell me the novelty in the paper?
Yes. So there are no experiments which deal with quantum networks or a hybrid classical quantum networks when it comes to synthetic aperture radars or complicated data. What we have are sparse experiments in relatively easy tasks like cats versus dogs or dogs, standard data sets. Very sparse research exists for complicated hyperspectral data or complicated SAR data, and the work on MSTAR or our new architecture or a new benchmarking architecture called HQuantSN do have significant societal value and can also be used for other tasks which are related.
So what were your contribution?
I formulated the HQuantSN architecture, and I have formulated the experiments which are associated with our paper.
Okay.
Yes, Kazar.
Yes, sir.
Yes. Results of your proposed study.
Yes.
Is there any comparison with the existing methodologies?
Yes, we have also used, the existing methodologies deal with resonate dense nets or standard networks for this data set. So we have trained them too, and we've also tested them out. So as it was seen for a standard ResNet, the ResNet gave us a better performance than quantum enhancements. But when it came to a standard DenseNet, we were seeing significantly better results for quantum networks.
Miss, from your proposed study that you got the better results than existing?
Yes.
Okay. Okay. Thank you.
Yeah. Thank you, Mr. Gajal, for your presentation.
Hello.
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 Yes, yes, yes.
Hello.
Any other
Yeah.
questions, sir? Any other questions from either session chairs and participants?
So I am Dr. Santosh. Yeah.
Sir,
Hello.
sir, welcome. Welcome back, sir. Welcome back, sir. Yeah, nice to have you, sir, in the session.
Yeah.
Yes.
So I would like ask two questions in that particular
Yes, sir.
presentation.
Yes, sir.
Yeah. So what kind of data set you have used?
We have used
What
the
kind of data set you have
MSTAR
used?
dataset. It's a SAR data set, and what we had were images which were pre-processed. It is called the Moving and Stationary Target Acquisition and Recognition data set.
Right.
And it's publicly
So
available.
based on that few data sets, so many research are there, right?
Yes, a lot of research has been done with, there are two specific distributions of this data set. You have one which deals with 8 different classes. You have one which deals with 3 different classes. And if you count a higher train test split, there are models which overfit and give you 100% accuracy. But if you use those same methodologies which we have leveraged here and we tested them in the same environment, the accuracy which we got are noted and the results were inferred from that.
Okay, good. Thank you.
Thank you. So shall I stop sharing?
Yes, sir. Yes, sir. Please stop your
Yeah,
sharing.
yeah.
And next, I request paper ID 295, Mrs. Sukandeep Kaur, to present her presentation.
Yes, sir. My research topic is evaluating generative adversarial networks for Gurmukhi handwritten character recognition. So in this presentation, we will discuss the introduction related to the topic and the related work, and in the generative adversarial networks and the types of GAN architectures we have used for Gurmukhi handwritten characters and the experiments and results. So this idea of using generative adversarial networks for Gurmukhi characters came from the use of deep learning. Like with the popularity of deep neural networks, there is a issue comes related to the lack of data sets, because for to train the deep neural networks, we need a larger data sets, which is not possible for the regional languages. And it is difficult to collect data set for such regional languages. And because this is the major requirement to train deep networks and to optimize the hyperparameters of deep networks. So many of the researchers have used some data augmentation techniques using distortions and additive noises to create such diverse data. And further, there is a latest approach, which is the GANs, to control over the generated data. So it generates a synthetic data which looks similar to the realistic data using some random values. So these are the some works which have used GANs other than generating the images. So like this, they have used conditional GAN and cycle GANs for image translate as image translators. And further, another researchers have used fixed text GANs for the license plate recognition. And another author have used deep convolutional GANs for visual recognition.
Sorry,
Similarly,
the slides are not changing with me.
Yes,
Is it
yes,
with
yes.
others
I'm
also?
just observing the same, sir. Ma'am, could you please turn on your slideshow view? Yes.
yes.
Yes,
Is it visible? Now is it moving?
turn on your slideshow view, ma'am, at your right side. And
Sir,
slideshow.
yes, I have done, but there was maybe some issue of, is it
Sir, is that okay for you?
moving now?
I'm asking respect to session chair faculties. Is that okay to you?
Okay with me.
Yeah. Yes, yes, sir. Yes, sir. Thank you. Ma'am, please continue your presentation.
Okay. So some of the others such as have used GANs for text to image conversions. And there is also another type, which is the conditional GANs. They have used for the recognition of camera captured document images. And there's also attention GANs, which are used for as intelligent making system. And yes, this is the another researcher have used GANs for synthetic data set and classification of scene images. Similarly, conditional GANs have been used for synthetic images of handwritten text, and WGAN is another.
Excuse me, ma'am, Mrs. Kaur, ma'am. Can you please make a relevance between your explanation and your slides, ma'am? Because it is completely contrasting what you are explaining and what we are seeing here.
Sir, maybe this issue is coming due to this full screen.
Manually better manage it. Manually, whenever you're speaking something about some slides, you better try to make it a relevance between your explanation and your presentation.
Okay, sir,
yes,
I'm now on this related work slide.
Yes,
is it
yes. Manually, you please operate it. Manually, you please operate it.
Yes, I was operating it manually, but with full screen, it creates some problem. Is it
yes.
Okay with this?
Yes, it's okay, ma'am. It's okay now. You are in related work slide now.
Yes, yes, sir.
Yeah.
So these are some of the authors have used various types of GANs like conditional GANs, fixed text GAN, these deep convolutional GANs, attention GANs for many applications other than the synthetic data generation. Similarly, for WGAN has been used with transfer learning. So basically, generative adversarial networks are the two networks. They have two networks. One is a generator, another is a discriminator. These two networks compete with each other like two players of min-max game. Means the motive of generator is to use the random values to generate images which looks similar to the original images of dataset. And the other network, which is a discriminator, it tries to distinguish between the real and fake samples. So these two networks are connected with each other because they uses the single loss function. As a discriminator uses the real as a data as well as the data generated by the generator, and using some distance measures, it distinguishes between the real and fake samples. It was invented by Goodfellow in 2014 for image synthesis. So in our work, we are discussing 4 types of GAN models: a deep convolutional GAN, Wasserton GAN, least square GAN, and conditional GAN. So in deep convolutional GANs, we have convolutional layers for the generator and the discriminator. So it uses the convolutional strides, and discriminator uses the convolutional operations, and generator uses the transposed convolutions to train the network. So discriminator has two categories of loss function. One is for the loss corresponding to the real images. Another is corresponding to the fake images generated by generator. And generator has a loss function for the generated images. So this is the architecture of DC GAN. It has like, these are the two networks, generator and discriminator. Generator uses a latent space or noise to generate the fake data. And there is a discriminator which takes this fake data as well as the real data to test it. Classifies. It is basically a classification, a normal any CNN architecture, any neural network, which is classifying this into two categories. One is the real or the fake data, and corresponding to that, it updates the discriminator's loss as well as the generator's loss. So there is another category, that is a Wasserton GAN, which is called the W GAN. It was invented by Martin based on the Earth mover distance theory, and to solve the problem of mode collapse and for stable training of GAN, because it changes the task of discriminator to regression problem, and it named this discriminator loss as a critic, where EM distance measure is used to distance between the real and fake data. And in this, a critic is updated multiple times as compared to generator. And it also uses weight clipping for discriminator to clip the weights to a given range. So the basic structure of every GAN network is same, like they uses generator as well as discriminator, but the only change comes with the loss functions or the input values. So here the loss is a certain loss which is used in discriminator as well as in generator. So there is another GAN model which is the least square. It uses the least square loss function at the place of sigmoid cross entropy, and in this it gives more stable training of GAN as it overcomes the vanishing gradient problem in simple GANs. So this has also a similar structure to DC GAN as the W GAN with this change in the loss function. So the another most popular GAN model is the conditional GANs. It other than synthetic data generator for image translation tasks, this has been highly used. And in conditional GANs, we can generate images based on some condition, because sometimes we want some particular kinds images. So in that case, in the generator, we insert another layer which is called the conditional layer, which will guide the generator to generate some particular kind images. So it has some kind of a control over the images, and it adds some condition with the external data to control the images to be generated and discriminated. Because every data has some additional information like class labels or image for image to image translation, that kind of conditions can be inserted in the generator. So this has a similar structure to DC GAN, except an embedding layer is inserted in this. So this is the GAN structure, CGAN structure. In this generator, along with the latent space, it also uses class labels as condition. And similarly, discriminator has a real data as well as the class label condition. And based upon this, it trains the model and generates the images. So for the experimentation, we have considered the data set of Gurmukhi handwritten characters, 7,000 samples we have taken, and it belongs to 35 classes. And every writer has written a single character, resulting into 7,000 characters, 200 per class. And pre-processing of data has been done to convert binary images into grayscale and to change the size from. So this is the results for the DC GAN. These are the images generated, and this was the generator and discriminator loss graph. So it has almost similar images to the original data set. DC GAN has performed very well as compared to other networks. So, but WGAN, we haven't found much better result with WGAN, and it also took a lot of time in training this. Maybe with some more optimization of parameters and training epochs, it will generate better results. So this is the CGAN, which is a conditional GAN. It also generated, you can see in these images that it generates a particular kind images in a structure. Like in every column, there are similar types of characters are generated. So it also results into a good image, good data generation. Another one is the LS-GAN. The results using LS-GAN was also not satisfactory. So there are maybe some more optimization may result into better data sets. So from this, we conclude that various variants of GANs have been implemented for the regional script of India, that is the Gurmukhi script. And these networks, it can be used to enhance the available data set of handwritten characters, because to train deep networks, we need a lot of data set with large variations. We can use these generated images with the original data set to train deep networks. And we have tried to optimize these hyperparameters, and the quality of these images can be improved using some simple pre-processing techniques of image datasets. And from these 4 types of networks, we found that DC GAN and conditional GANs have resulted into more efficient synthetic data generation. And it can be further, these networks can be further explored to improve the quality of data generated and to generate the data for some other index scripts. So these were the references corresponding to the work. So this was all. Thank you. Any questions?
What are the different quantitative measures that you have used?
Okay, sir, we have considered the quality of images that was generated, that whether these are the shape of the characters is similar to the original data, because in this, that is very easy to distinguish between the original data set and the images generated. Another was the loss functions, generator and discriminator loss, that up to if after some time it doesn't change much, then we stop the training. And based on these 2 factors, we have
Looking at only at the images, it will be difficult because you will be having too many images in the data set. So you should be able to quantify your results, maybe in terms of accuracy or precision, recall, F score. So that would be better to say that a particular model is outperforming the others. The other question was, what is the novelty in this paper?
So actually, we are trying to use these generated images, as you told that we should measure these their performance by using these generated images into training of deep networks. So the novelty is that we tried to, because before that we haven't found any work which have generated the Gurmukhi characters using these networks. So we tried to explore this method to generate the synthetic data set, so that with the in future with some modifications we can use them in training the networks.
Okay.
Yeah, I think I would like one question.
Yes.
Yeah, I'm audible or not? Just check it.
Yes, sir. Yes, sir. You're audible.
So, what kind of means customization you have used in that particular Gyan approach for your research work?
Sir, for these, we haven't used any further customization. We have used the basic structure of CGANs, whether in conditional GAN also, the simple structure of the normal conditional normal structure is used, GAN structure is used, because we want to check the various variants of GANs. In future, we will try to do some customization in this GAN networks.
Is there any other questions, sir, from either session chair or from the participants?
Yeah, please.
Yeah, ma'am, thank you for your presentation. Sir, we are having our last presentation, paper ID 394, presented by Mr. Rishabh. So, Mr. Rishabh, sir, you can share your screen and presentation. Hello. Rishabh Hansilia, sir. Hello. Hello.
Hello, sir. Am I audible?
Yes, you are audible, sir.
Yes, sir. I'm present.
Yeah.
So, good afternoon, everyone. I'm Rishabh Anselia, student of Triple IT Bhagalpur. I'll be presenting on the topic detection of malaria by using a CNN model. So, the presentation will follow the following sequence. I'll start with a background overview. So, malaria continues to be a major health concern around the world, affecting around 200 million people and resulting in over 400,000 fatalities each year. There are over 100 different Plasmodium infections, but only 5 of these can cause malaria in humans, namely Plasmodium falciparum, Plasmodium malariae, Plasmodium vivax, Plasmodium ovale, and lastly Plasmodium knowlesi. Only 2 of these 5 are hazardous to human, namely P. falciparum and P. vivax. So when a Plasmodium enters a human body, it targets and attempts to damage the red blood cells and liver. It's critical to get medical attention as soon as possible, since malaria has a particularly high risk of causing serious illness in young children, babies, and pregnant women. If diagnosed and treated early, malaria can be reduced and deaths can be prevented. Malaria can be easily detected with a blood test, but your physician might also consider a physical exam and ask you relevant questions about it. So since everything is now done by computer, since it provides more accuracy and computing power in just a blink of an eye. So one of the most difficult challenges that hospital face is providing the best treatment to patients at a fair cost. So we'll be using computer for this, and also due to the recent breakthroughs in cognitive computing, deep learning, machine learning, and soft computing, with these can be employed to use computer-based information. So the prime objective of our research is to encourage the early detection of malaria parasites by using a convolutional neural network on malaria dataset available on Kaggle to train the model. After training, the model can be acquired as a package, which can be further used as a mobile phone app, which the user receives a result after uploading a picture. To use the model on a smartphone, can convert it into a TensorFlow Lite model, which is more efficient because of the computational capacity which are available on smartphones. Now I'll be continuing with literature survey. So we considered a lot various research publications which included machine learning, deep learning, and other fields, including smartphones, a use of smartphones with the microscopes to analyze the images of blood smears to detect malaria parasites. So first one is Linda, which employed morphological factors for feature extraction and principal component analysis. He found that STMM provided a accuracy which was lower than other methods like CNN. Rajaraman implemented a feature extractor for sorting parasite and uninfected blood cell to aid illness detection using a previously trained CNN model. Liang reported a detection accuracy of 97.37% with their 16-layer CNN model. Rosado described a supervised classification-based image processing and analysis method for detecting P. falciparum, trophocytes, and white blood cells in GM-sustained thick blood smears. Cesario discussed the use of mobile support for vector-borne diseases in places where professional medical care is unavailable. Jain and Carpenter proposed a faster RCNN and object-based detection based model based on CNN. Researchers have created a mobile app that can instantly identify malaria by taking images of a blood sample. This one is called Mobala. Now I'll be discussing the problem description. So the most common way to diagnose malaria right now is by a technician, by use of a technician which examines the blood smear under a microscope. This form of diagnosis is based on expertise and understanding of the individual experimenting. So that's why we want to automate this process using modern deep learning tools, because manual processes are time consuming and prone to human error. Our approach should also allow for future training with more data and might be used as a smartphone application. So the methodology we use follows in two stages. First one is dataset summarization. So the dataset we use is called the malaria cell image dataset. It contained 27,558 cell pictures with an equal number of particized and uninfected cells. It was divided in two parts. So two categories, they were parasitized and uninfected. So there were in total 30 and 780 photos in each category. Out of these, we used 11,024 photos to train our model, and 2055 for testing. So we divided our data set in 80-20% for training and testing respective. Second stage is the use of a convolutional neural network on this data set. So as a part of a CNN pseudocode that required data set train, afterward the model is evaluated on the data set. The model's output will include accuracy, recall, precision, and a F1 score. So this is the algorithm we use for CNN model. The CNN model we use, the machine we used had the following specifications. And as I mentioned before, it was divided. Data set was divided into 80-20%, and the measures are in the form of accuracy, recall, precision, and F1 score. So now I'll be showing the results. So we received an accuracy of 96% in our testing. Same for recall 96%, 95% for precision, and 0.954 for F1 score. So these are the graphs, accuracy graph and loss graph. So when comparing the performance of proposed work for malaria detection to existing machine learning techniques, we may find that our proposed model outperforms other classical methods. So concluding, in medicine, there are much too many manual works, even for doctors. Determining an illness from raw data is tough, which is why many healthcare businesses are turning to machine learning and deep learning technology to do so. We can provide clinicians with greater information while caring for patients using advanced analytics like these. The practitioner or internist at the bedside will gain from deep learning. Machine learning can provide objective feedback to boost efficiency, accuracy, and reliability. Medical practitioners will use models like the one proposed in our study to improve current facilities in malaria detection area, as well as other related domains. So our model may also be further trained on vast amounts of data and better computers with high processing powers as our data set grows in real time, resulting in increased accuracy and efficiency. So these are the references. Thank you so much for your valuable time.
Rishabh, you are claiming in one of the slide that your model is performing outperforming the existing state of art, but I could not see the results of the state of art in that particular table where you were showing the precision recall F1 score corresponding to your model.
Yes, I am not sure, and I will tell you the values, sir. We use other classical algorithms like KNN. It showed accuracy of 0.94. Others were like a linear regression. It showed 0.943. Naive Bayes showed us a 0.85, and random forest SVM showed a 0.788. Random forest showed 0.96. Sir.
What is the meaning of precision in your model?
Sir,
What does it represent?
Sir, for like precision is basically sir true positive upon true positive plus false positive. So with considering malaria, sir, it is the one like which we identified correctly, and also were they were uh, positive with malaria, like parasitized upon parasitized plus which we identified as parasitized but were not infected.
1, 2, 3.
Okay.
Thank you, sir.
Yeah, I think.
Sir, should I?
I would like to ask 2 questions.
Yes, sir.
Yeah, one question: what kind of data set you have used, and this data set is available open sources data set, and what kind of state of arts methods are there to compare your findings?
Yes, sir. This is an open source data set, sir. It's available on Kaggle. So this is an image data set, and it contains 2 types of images. One is parasitized, and then one is uninfected, sir.
So I think in that data set is an image data set, right?
Yes, sir. Yes, sir.
So in image, what kind of objects are there? Means patient as
sir, it would be like a image of a cell, and in that image, you would find like a small a different colored objects between it. Like for an example, sir, in a cell there is a nucleus. So like you can identify a nucleus, right? So it will find something like a different objects, foreign objects. So you can identify it as a parasitized.
Okay. So this is a label data, right?
Yes, sir.
Okay. So for label data, what kind of features are you going to extract from this? Means have you any kind of information?
Sir, they were like they color it with some kind of chemical, sir, and with the blood smear, and by that it detects those small parasitized portions.
Okay. Good. I think you have to work hard. This work is done by several researchers, right? And they publish actually that work is with accuracy, right? I think.
Okay.
I have actually gone through several papers. You have to work hard and add your contribution, right?
Yes.
Okay.
Yes, sir. Thank you. So should I stop sharing?
Yes, you can stop sharing. Thank you, Mr. Rishabh, for your presentation. And
You're welcome.
Sir, with this presentation, we were done with all the presentation in this particular session, sir. Now I may request all the session chairs and participants to turn on their videos for a group photo, sir. If possible, please turn on your videos for a group photo. I request all the session chair persons and participants to turn on their videos for a group photo. Thank you, sir. Thank you, everyone. Thank you, sir. On behalf of NIT Raipur and organizing committee of the conference, I thank you all for sparing valuable time as well as providing valuable insights to the.
So thank you, Shul sir, for your kind help. We conducted this session, right? Later, I think I joined this session because I was busy with some work. Okay, thank you very much, and all the participants. I wish you very happy and prosperous future for your new findings in your life. Thank you very much.
I'm thankful to all the organizers who called me to chair this session. So best of luck to all the participants for your future endeavors.
I marked the absent in 15 and did it in 21. 21 अभी no, एक response अभी बाकी है.